Alors, bonjour tout le monde. Donc, ça me fait plaisir de vous présenter notre conférencier d'aujourd'hui, Simone Dalla Bella. Avant de dire quelques mots à son sujet, je veux juste vous annoncer que c'est notre dernière conférence habituelle mensuelle de cet automne. La semaine prochaine, l'événement terminale pour qu'on reprenne cet hiver nos conférences, ça va être la journée scientifique de NeuroQAM. Donc, le 6 décembre, qui va se faire ici dans le pavillon. Donc, vous êtes tous et toutes invités à y venir et tous les détails sont sur le site web de NeuroQAM. Puis, on va reprendre la série d'hiver de conférences mensuelles en janvier. Oui, information privilégiée.
Pas encore inscrit déjà, vous avez vraiment jusqu'à aujourd'hui, comme après la conférence, pour vous inscrire puis avoir un lunch. Si
Ouais,
vous inscrivez après, ben, il va falloir amener votre lunch.
c'est ça.
Ouais.
Parfait. Excellent. Alors, donc, un petit mot sur Simone qui est italien d'origine. Il m'a dit il me demandait en quelle langue de donner la conférence, en français, en anglais ou en italien. Donc, ça, je pense que ça va être en anglais. C'est mieux que. Il y a juste Mario pourrait nous traduire en ligne, mais on va l'écouter en anglais. Ça va être plus facile. Donc, Simone est italien d'origine. Je pense d'abord étudier en psychologie cognitive à Padoue. J'ai retenu quand j'ai lu ta bio parce que vous savez, Padoue, c'est une des premières universités en Occident. C'est la troisième, mais il s'obstine tout le temps. C'est laquelle? Deuxième? Ah, deuxième, l'italien dit c'est le deuxième, mais tu demandes à un autre, un français, il va dire c'est la troisième parce qu'il y en a un autre, mais c'est pas grave. Et ensuite, il est venu ici à Montréal pour faire un doctorat à l'Université de Montréal avec Isabelle Peretz. Donc, évidemment, sur la musique, des pianistes de formation, je pense. Hein? Voilà. Et on s'est croisés dans ces années. Je ne sais plus qui finissait ou quoi, mais on était à l'Université de Montréal il y a quelques années. Bon, c'est ça, quelques années. On laisse le suspense. Et ensuite, il est parti aux États-Unis faire un postdoc avec Catherine, comment elle s'appelle? Palmer. Caroline Palmer. Il est revenu à McGill encore et il a fait un petit détour par l'Europe, puis finalement, il a compris que c'était à Montréal qu'il fallait revenir et faire sa carrière, chose qu'il a fait ou fait. En fait, il est professeur titulaire du département de psychologie de l'Université de Montréal. J'ai peut-être déjà dit, mais sinon je vous le dis. Et en fait, on l'a appelé, dans les faits, c'est que le Brahms, vous connaissez peut-être le Brahms, puis je suis pas capable de dire l'acronyme, là, le Centre international de musique. Ah, il est là, voilà, le Brahms. Euh, donc, avait besoin de renouveau et il est, depuis ce temps, co-directeur avec Robert Zatoré du Brahms, qui est un centre très rayonnant sur la neuropsychologie, les neurosciences de la musique. Il est titulaire d'une charte du Canada sur le titre, es-tu là? C'est quand même, ouais, ouais, ça ressemble un peu à ça, là, donc les compétences musicales visuo-motrices et les nouvelles technologies ou quelque chose comme ça en français. Donc, il y a un beau dossier de publication avec des articles, certains articles très influents, très intéressants, dont qui tournent autour du rythme. C'est une composante au centre de tes travaux des dernières années et on a très hâte d'entendre un petit peu plus sur les applications. Tu as fait beaucoup de recherches fondamentales, mais j'ai l'impression que tu fais un petit peu plus de recherches appliquées. C'est ce que tu voulais nous dire. Donc, merci d'être là, Simone.
Tout d'abord, merci beaucoup, Dave, Isabelle, pour cette invitation. Je suis ravi d'être là aujourd'hui parmi vous. But I'll switch to English. Otherwise, it's going to take 2 hours for me to present to the content. So the idea is to talk about musical rhythm, which is an important component of musicality. We have other abilities, but rhythm is such an important one that we all share. We don't have to be musicians. Some of you are probably musicians, but rhythm is all-encompassing and present in everybody. So I'm going to talk about that. And the talk is going to be divided in two parts. First of all, I'm going to focus on rhythmic abilities. What are rhythmic abilities, how we study them, and what we know about that. And we have a few research work in the lab that I will present to you. In the second part, I will focus, okay, how can we use rhythmic abilities to train different clinical populations? And I will give you examples from Parkinson, from ADHD, and other populations in that regard. So bear with me. When we think about rhythm, very often we think about something very specialized, right? We think of dancers who basically move artistically to the beat of music after many years of learning and training. But rhythmic abilities are much more common than that. We find this in certainly not artistic situations, in all cultures, in very mundane kind of situations too. And I'm pretty sure that some of you may, do some jogging in the morning. You take your smartphone and probably you run or walk to the beat of music, even without being completely aware of that. So this is the kind of ability that I will focus on today. First of all, there is a very tight link between rhythm and movement. This is universal. Dance is present in all cultures. Is very natural in the general population. So if you ask people in a group, you can do this in a class, you just tap or walk to the beat of music. Most people will be able to do that in a quite good way. It's very ancient from an evolutionary standpoint, this capacity to integrate perception and action, especially when there is a common timekeeper, which groups, for example, can synchronize with. Is precocious. Within the first year of life, we have the basic milestones, capacities, which allow people to perceive the beat, perceive even complex rhythmical structures, and later on, around 2 years and a half, to move along with that. And we know that these abilities are sustained, I will come back to that in a second, but sustained by cortical subcortical networks. So there are some networks which are quite well known to support beat perception, rhythm perception, and movement. So about what is rhythm? I mean, I don't know if some of you are musicians. Some of my students here, I know they are. But just to give you the definition in a nutshell, we can simply say that rhythm is linked to temporal patterns which result from the organization of sounds in terms of duration and intensity. So it's very basic at the end of the day. So it's enough to have some durations, some accents, you put them together, you mix them, you get something regular, and then it sounds rhythmical, right? It's true for music, but it's also true for speech. I'm pretty sure that most of you can speak rhythmically just by playing with durations and intensities. So here is an example, which sometimes I present this talk in summer or in March. But this is very appropriate today because, so what I'm asking you to do, think of this music that you know very well. Of course, this never works. Okay, some of you are bobbing your head. So you got it, right? This is the beat. These are strong beats. And so automatically we can catch that and we can move along with that. What's interesting in this aspect of music, in this case, well, it's periodic. The beat is periodic. It occurs roughly at the same intervals, is regular. And we know from both theory and also research in neurocognition of music that this helps direct attention towards expected moments in time, which is a process which is stimulus-driven. Let me explain you what this means. So imagine that. And the brain works pretty much like that. We have internal oscillations. Think of an attentional oscillation, when you just receive stimuli from the environment. And at a certain point, it is an external stimulus. So here there's the internal oscillation. This is external stimulus, which is presented. What's happening? What you see, the internal oscillation starts slowly to entrain, to couple with the external stimulus, to the point that the maximum attentional energy occurs at the moment of the external stimulus. So rhythm can capture our attention, and neural oscillations are the substrate of that kind of process. I will not have time today to dig into this part, but there's a lot of literature on this part. But the good news is that when we stop the external stimulus, then we can predict when the next stimuli are arriving, which means that, for example, if we have to do an action, well, we can move at the moment of the predicted rhythm, and this can help us. There is evidence about that. So what is the neural circuitry which is supporting these processes of bit perception? So this is a general model which actually has been proposed a few years ago. There are others, but I'm just presenting this one for the sake of simplicity. You see a few areas: subcortical and cortical, basal ganglia, thalamus, cerebellum, auditory cortex, prefrontal cortex, premotor cortex, and this is supplementary motor area. These are all areas which are connected in networks. You can see at least two networks here. And so when we do beat extraction, so if I presented you a musical stimulus like the one that I presented you before, and you just extract the beat, well, you roughly engage these areas. Of course, the auditory cortex is an auditory stimulus, no surprise, but also the basal ganglia, and also, for example, SMA. Now, you don't move, you do nothing, right? But in another situation, I may ask you to move along with the beat. You can clap or just stop. What we call, technically speaking, perception action integration, synchronization, there are different words for that. And now you see there are other areas. Of course, the auditory cortex is always involved, right? When you move to the beat, you perceive. But then there is the cerebellum, and there is also the premotor cortex, which is more relevant for auditory motor integration. What's striking in this picture? Well, if we do action, if we move along with rhythmic stimulus, well, it's pretty normal that there are areas like the cerebellum, which are typically motor areas activated. But when we just do nothing, we just listen to rhythm, there are still areas like the basal ganglia and there's SMA, which are activated, which is a bit odd because these areas are not certainly linked per se with perception. So it seems like there is quite a nice link between the properties of rhythmic stimuli, auditory stimuli, and the motor system. This again underscores the fact that there's a very tight link between perception and action. So basically, it's enough for you to listen to a rhythmic stimulus without moving, just so that your brain still activates its motor areas. That's very important because it can suggest that we can use rhythm, just perceptually even, to activate or reactivate brain areas which are linked with motor control. And so we can use rhythm as a way to, for example, recover lost functions in populations. Okay, what I'm going to do here, we'll use a translational approach. This is what actually Dave hinted to before. So I will start from fundamental research. I will show you some results from fundamental research, focusing on, so how do we measure rhythmic abilities? What are, what we observe in the population, general population, not necessarily musicians. And then we use this fundamental research to do applied research. So to use this knowledge to devise, for example, rehabilitation strategies, which are now theory-driven. And to give an additional spin to that, well, this is bidirectional. It's a typical translational approach. So we apply this to clinical research. Clinical research informs fundamental research. So we will know more about the mechanism. But the spin is that this is supported by technology. So we'll use 21st century tools like mobile devices to enforce this, this relation. And by doing that, we are also using gamified approach and serious games that we'll talk about in a moment. Okay, so let me start with the first part, which is about measuring rhythmic abilities and finding a way also to capture individual differences in this capacity. So we may ask, how do we measure rhythmic abilities in the lab? The thing is, it's not by accident they wrote abilities, not one. There's not one rhythmic ability that you can measure with a simple task. There is a bunch of them. And so we need a few tasks to be able to capture those abilities. Many studies in the past have been conducted just using one method. And sometimes the picture you get is very limited to that specific method. So it's important to have a battery of tests. So this is what we started to do actually before 2017. Actually, this is a project which started from 2011 and even before. So we developed a battery, which is called the Battery for the Assessment of the Auditory and Sensory Motor Timing Abilities, BASTA. For those of you who are French-speaking, should ring a bell. And actually, this was completely intentional. There's no, it's pun intended. There were other batteries which, was started to be developed at the time, but this is what we basically developed. The battery includes perceptual tasks. I will scan them very quickly. In one task, we do duration discrimination. So we present two durations, and the participant has to say which one is longer or shorter. In another task, we now present rhythmic sequences in which we have sequences of pure tones, just a metronome, or short musical stimuli. And we ask people to say if the sequence is regular or irregular. So I give you an example here. It works. See that there is a bit of an irregularity inside, and it's correct. There is one. And so we have this kind of stimuli. All these methods use an adaptive approach. So sometimes the difference is bigger or smaller. So we get a threshold out of these tasks. And then another task, which is quite popular now, is the beat alignment test, originally developed by John Everson and Annie Patel. And the idea here is that you will listen to a segment of music, and there is a superimposed metronome. And you have to say if the metronome is on the beat or not. Okay? This is how it sounds like. Some of you bob their head like that. Indeed, it was not aligned. Not a big difference, though, but not aligned. Another example of that. Okay, that's better. Okay, this was aligned, and so forth. So then we have a few tasks which are more sensory motor tasks. We use as a model finger tapping. Okay, participants have to tap on a surface, sometimes without a stimulus. It's what we call unpaced tapping. They tap with a metronome in another condition. They tap with music. And also we have a couple more tasks that I will not talk about much today, but just for the sake of just providing a full picture. This is a task it's called synchronization continuation. People tap with the stimulus, and then they have to continue when the stimulus is over. And adaptive tapping is basically a task where people tap, but then they have to follow stimulus, which can accelerate or decelerate. So this sort of sensory motor flexibility task in this case. Okay, so when we started to develop this battery, it's a usual battery that we developed in a lab, right? With 150 cables, which of course had to be adapted to the devices that we had at the time. Now we developed with time a more efficient version, which is a tablet version of this battery, which is actually now commercialized. We tested more than 700 participants across the board in various populations. So musicians, non-musicians, older, healthy adults, but also a variety of clinical populations, going from stroke, Parkinson's disease, neurodevelopmental disorders, and also ADHD, dyslexia, autism. The good news is that this year we published norms for this battery. These are adult norms. To my knowledge, it's the first battery that has been normed in rhythmic abilities to date. And so you can take a look at the norms. They are published, they're available. So you can use them if you want to, determine if you are good or bad on a rhythmic task, but also with clinical populations. It's very good to have norms. You don't need to have a control group in most cases. Now, what came out of these norms too is that we devised what we call the beat tracking index. We proposed this composite score, which are very good indicator of beat-based rhythmic abilities. It's a proxy. And because the battery itself is very long, it's 2 hours. I mean, you cannot run a battery of 2 hours each time you want to know if somebody is good or bad in rhythmic abilities. You need, especially in clinical populations, it has to be shorter. So how does this work? The beat tracking index is based on 2 tasks, the beat alignment test that I presented you before and pace tapping. And I'll show you data in a second, but this measure captures the variability spectrum in rhythmic ability. So here you have what you would get from the beat alignment test. This is in Z-score, but you see the range of variability, and this is what you have in tapping. And the 2 of them actually are correlated, but by combining the 2 of them, actually we have a good appraisal of the general variability of the population. In this case, is more than 100 participants on rhythmic tasks. And you see the full distribution. It goes from some people who really have issues to those who are extremely good in rhythmic ability. The good news is that it takes 10 minutes to obtain this measure. And it has very high test reliability, so about 0.85, which suggests that we can use it in clinical settings on top of other tasks. Okay, now BASTA in general is sensitive to individual differences, and I'd like to show you a few examples here. So for example, it can detect rhythmic disorders. There is some literature on rhythmic abilities in the general population, most of us. And we find out that basically some people in the general population have problems with rhythm, right? Either they cannot move to the beat or they cannot perceive the beat. It's just a minority. But there is a certain literature on this aspect. So I'm showing you, for example, some data. These are data from a previous study. This was about on 20 participants, non-musicians, all of them. And with the beat alignment test, you see that there is a certain degree of variability in the performance in this task. And some people seem really to have issues with this task, right? This second study that we published in the same year is now focusing on beat deafs, what we call beat deaf participants. These are people in the general population who have really a hard time in catching the beat and in moving along with that. And in this case, we see, as compared to healthy controls, a very small control group, these participants here were having difficulties in beat alignment test. The same picture is found now when we focus on tapping performance. So here again is a group of 20 non-musicians tested when they were tapping with metronomes, different speed, and also with music. And you see that most people can do it, actually. People are very good. These are non-musicians. These are people without musical training. But some of them, well, again, seem to have a bit of problems, and especially with the musical stimulus. Right? Now, again, we can go back to our beat deaf group, and we find out that there is, among these participants, there is just one who really is bad with perceiving rhythm, especially in the context of musical stimuli. So the task is the battery is sensitive to those individual differences. And then based on that, we conducted recently a study which is tailored to test the effect of formal and informal musical training, because people who have poor synchronization and beat deafness are the end of a continuum. But what's happening in between, right? So are all the others extremely good? And how people vary in the general populations. And can we identify profiles of rhythmic skills And perhaps this profile of rhythmic skills are also linked with other cognitive functions. That's another interesting question that we are addressing now. So how do we do that? How did we do that? We used BASTA to collect data from 80 participants, 40 musicians and 40 almost non-musicians, and we use machine learning to try to learn more about their rhythmic profiles. So we use a method which is called sparse learning and filtering. So with the idea of selecting a minimal set of BASTA measures. So in other words, if we have a bunch of tasks, which of those tasks are really sensitive to distinguishing a musician from a non-musician? Can we predict a musician from a non-musician just by using a few rhythmic tasks? Or we need a bunch of them? Or maybe we need, it's not enough, you know, because a musician is just rhythm related. So what we did in these groups of participants, we selected the full set of variables that we get from BASTA. It's a lot. See, 7 perceptual, 48 motor. We use this machine learning method, and then we got 2 models which selected 5 variables and 4 variables here. So see, much less than what we really have at the beginning, to account already for 84% of the variance. That's a lot. And then we combine them because we wanted to get really the best of it into a model which is called model PMI, perceptual motor interaction. Not very original name, but it works. And so the model with just 2 perceptual and 2 motor variables plus their interaction is also important, has an accuracy of about almost 90%. So basically and you will see in a moment, on just very few tasks, you can determine if somebody is a musician or a non-musician with very good accuracy. So how does this work? So what you see here is a composite score of those perceptual tasks which are part of the PMI model. I will tell you in a second what they are. And on the y-axis, then you have the composite score for the motor tasks. So then we computed profiles of rhythmic abilities, which seem a bit odd here, but this is just a seemingly complicated representation of something very simple. Here we have 4 variables coming from basically 3 tasks, which are sufficient to identify if somebody is a musician or non-musician and to define a profile. These variables are, for the perceptual variables, the bit alignment test, you already know what it is, and also the threshold in an isochrony detection. And for the motor variables, is basically tapping tasks. And is basically how close people are to the target when they tap with the stimuli. Now, so it's a combination of this perceptual and motor variable which define the profile of a musician. Now, you see that there are different things here. So some dots are greater than others. It means that these variables are more important for the profile, for the musician. And when the interaction here is bigger, means that the interaction between these tasks is also more important. This is what we get with non-musicians. The profile is different and can be easily discriminated by the PMI model, so with a very high degree of accuracy. And you see that there are some visible differences. So for example, here there's no as much connection between motor and perceptual dimensions, and also the motor dimensions are more important for the non-musicians than for the musicians. Now, if we go into that a bit more, let me just dig a bit more into the details. So what you see here is that basically, not only the model is good at distinguishing musicians from non-musicians, but it's also very good at explaining the internal variability within musicians and non-musicians. Just to give you a normal example. So think of a regular non-musician, most of us, right? But there are people who are very good in rhythmic abilities and people who are less good. There is this internal variability. Some people are as good as musicians, right? Potentially. If this is discovered early in life, they may go into music because they may be probably successful in learning music, right? So the model is doing a very good job in doing that. Let me explain you what you see here. So these are the 4 variables which compose the profiles, the graph. And so you see the variable value for each of the dimension. And then here is the prediction of the model. When it's 0, well, this is very likely to be a non-musician. When it's 1, this is very likely to be a musician. And now you see that the greater the value of this specific variable, the higher likelihood that this is going to be a musician. Right? So you really have non-musicians here who are true non-musicians. But you have some non-musicians here who are, getting almost like musicians. And the relation is striking for the motor variables. This is quite amazing. I mean, you see, you can explain 61%, 65% of the variance just by taking one variable within the group of non-musicians and musicians. So this model is quite powerful. So we decided, okay, fair enough. It's probably trivial to distinguish musicians and non-musicians. So what's happening when we take only non-musicians and we want to see what's going on in non-musicians? It's the majority, after all. So we want to know if there are subgroups of non-musicians. So we did cluster analysis, and it happened that we came up with 2 subgroups within non-musicians, which have 2 different profiles. And one of these subgroup 2, is closer actually to musicians. So among non-musicians, it happens that some of us are probably more musical than others. And this model is capable of distinguishing that. And it seems like that this relation is linked with what we call informal musical activities. So for example, if some of you are going to choirs or just to amateurishly learn a musical instrument, well, you're more candidate to being subgroup 2 and potentially also to be, to develop good rhythmic abilities in the future. Okay, you may say, fair enough. We are very interested in musicians and non-musicians, but so what else? Well, we know that rhythmic abilities are generally also altered and vary a lot in clinical populations. It's surprising to see that rhythmic abilities are disrupted in a number of clinical disorders. Parkinson's disease, stroke, ADHD, dyslexia, speech and language impairment, developmental stuttering, mental coordination disorder, last but not least, autism spectrum disorder. All of them have some degree of rhythmic impairment. You may say it's an accident. I say, not sure. It's an interesting accident in any case, which suggests that either there is a common process, which is underlying rhythmic abilities, which is present in all these disorders, or indeed that there are some areas of the brain which are so fundamental that they are touched by each of these disorders. And so we can think more about that. So how can we remediate that? Let me give you some concrete examples from my own lab. We did a lot of work on Parkinson's disease. So just a couple of words about Parkinson's disease. It's the most frequent and severe of movement disorders. There are 4 million cases worldwide, and the number of cases is going to double by 2030. So it's quite an important issue. It's a neurodegenerative disease. Unfortunately, there's no cure for that, which is the result of neuronal depletion and generally the regulation of the dopaminergic system. There's a few motor symptoms that I'm sure you are aware of, like the common resting tremor, slowness of movements, absence of initiated movement, and general rigidity. Another problem that we observe in Parkinson are also gait disorders. There is an whole bunch of work that we did on that part, but I'm not going to get into that because otherwise I will stay here for 3 hours. But I want to mention one thing, is that one characteristic of Parkinson's disease is that the disorder is linked also with rhythmic disorders in general. And this manifests in different areas in production. So if you ask a Parkinson patient to tap along with a stimulus, even a simple one, you will see a disorder. In orofacial coordination, so if you ask a patient with Parkinson to just reproduce a syllable or a sequence of syllable like pataka, 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 you will see slowing down and sometimes performance which is certainly not the one of controls, and also gait. So the typical gait pattern of Parkinson is a slow down gait with sometimes blockades, freezing phenomena that you can observe. But the problem is not just motor. Parkinson is a motor disorder, but we also see a problem in rhythm discrimination, detection of tempo changes, and also detection of beat alignment, which is what is tested by BAT. So it seems like the problem is not just purely a motor disorder per se. And this is why we talk about a general dysrhythmia in Parkinson, and this is something which is all-encompassing. So just to give you an example of a study that we did with my former PhD student, Frédéric Pujarinet, in France. So this is, in this study, we took a group with patients with Parkinson, and we asked them to do a few tasks, tapping task, orofacial rhythmic tasks, like the one I was mentioning, when they had to reproduce sequences of syllables as fast as possible, and also gait tasks. And what you see here is the variability in the performance of this motor task. And you see that the two of them are correlated. So somebody who's really very variable in this orofacial articulation task, while the person who is also very variable in the manual task, which are two different factors. So in the interpretation is there may be a common cause of that. We see this with gait and manual. We see this with orofacial and gait. All of them are correlated, right, in an interesting way. So what we wanted to know, okay, where does this come from? There seemed like there is a general dysrhythmia. Where is there, a reason for that? So what we wanted to do was to check, okay, can this be explained by their performance in rhythm perception? As we said before, rhythm perception engages motor areas. We may predict that rhythm perception as a proxy towards understanding the functioning of the rhythmic system can predict also what's going on at the level of the motor outputs. And this is exactly what we see. So we run here the beat alignment test, and we find out that basically those who have the greater probability of being variable, I would say, those who are more variable are also those who have the lowest performance in the rhythm perception task across the board and across the domain section. Now, another example I'd like to give you is the one of neurodevelopmental disorders. So what you see here, this is a recent paper published by Miriam Lenz, in which basically you see the percent of individuals basically affected by, on average, by impairment in rhythm or timing skills across the board. You see that it varies, but all of them seem to have some degree of rhythmic or timing impairment. And there's been proposals that this rhythmic disruption may indicate a typical development, maybe a marker of a typical development. It seems like understanding these disorders is key in clinical setting. And with the goal, for example, to identify risk factors very early during development and perhaps creating personalized interventions later on. I'm giving you two examples from my own lab. This is a study that we ran with Frédéric Pujarinet again. This was done in children and adults with ADHD. And what we see here is basically that a group of children, I think it was about 40, with ADHD are impaired in a variety of timing and rhythmic tasks. We use BASTA that you already know. So for example, children and adults were impaired, for example, in the beat alignment test, very clearly. And also in other tasks like detecting irregularity in a musical stimulus, and even in detecting different durations. Similar the deficits are found in tapping tasks. So it's all encompassing, right? It's a disorder which touches production. So here is synchronization, is pace tapping. You see generally that ADHD are impaired in basically in tapping tasks, also adults, children and adults, relative to controls. An interesting finding here, and then it's that can be developed further, is that, well, there is still a lot of variability in these rhythmic abilities. BASTA allows us to capture this variability. So here what you see is the performance in the butt and the performance in the pace tapping with the different groups. Blue are controls, red are children and adults with disorders. So there is still a lot of variability. The groups are quite distinct, but some children perform better than others. And so we may wonder why. And we found out in this paper that basically this variability seems to be linked to general cognitive functioning, like executive functioning. So those participants who were more capable of either detecting a beat or moving to the beat were those who were faring better in tasks of flexibility and inhibition control. So it seems like there is this nice link with other cognitive functions. Finally, before I move on to the second part of the talk, here we conducted another study. This is my other former PhD student, Valentin Begel, who's now in Paris, who basically conducted the study. This was done in collaboration with Delphine de la Cherie in Lille. And the idea was to run, again, these tasks, perceptual and sensory-motor tasks from BASTA in developmental dyslexia in children. And again, we find similar disorders, right? Again, with the same exact task, with the beta alignment test, we see that children with dyslexia perform definitely lower than match controls. Then this deficit extends also to the motor performance, so to tapping tasks. You can see this clearly here with both metronome and music. And interesting, again, we see a link with executive functions. So those participants who are faring better in the beta alignment test or the pace tapping task are those who also have higher scores in terms of flexibility in this specific case. Okay, so I hope that I showed you a bit spectrum of what we can do in terms of tested rhythmic abilities, and that there is this variability that we start to account for using models, but also trying to make a link between those rhythmic abilities and other cognitive functions, right, which also can be related to that. The causal relations is not obvious. This is something else, but this is why we need intervention studies. So let me now move to training rhythmic abilities. Let me go back to what I said at the beginning. So we know that moving to the beat engages neural networks related to motor control. And now we know they're also linked with executive functions. So we may think that by training these rhythmic abilities, especially in populations who have disorders of rhythmic abilities, we may lead to causally improve other functions like executive functions, such as inhibition control and set shifting. Of course, here we are doing a causal inference based on previous correlational data, but this is what actually intervention study is for, right? Now, we know at the same time that there are beneficial effects of rhythmic training in patients with movement disorders. We have contributed to this literature pretty much too, in Parkinson's disease. I will not go through that, except one study, but not with the standard method that is mentioned here. Also we have a positive impact of rhythmic training on inhibition control in other more developmental studies. There are reasons to believe that, well, by training rhythmic abilities, we can have a transfer towards cognitive functions. How does this work? So we know that there is these areas which are responsible for beat perception, rhythm perception, and synchronization. We can train them in a very easy task just by tapping. If these areas are shared with other motor effectors and is also shared with, for example, other cognitive functions, well, we should see a transfer effect towards these other motor abilities, walking, speaking, but also we may see further effect towards cognitive functioning like inhibition control. So I'd like to provide evidence for you that this can be achieved, and in the next slides. Now, to do that, to implement this idea, we use a gamified approach. So why a gamified approach, and what is that? We use what we call serious games. Maybe it's the first time you've heard this term. Why a game should be serious? If a game is a game. Well, a game, it can be serious in the sense that it can be designed for a purpose other than pure entertainment. And I'm sure that most of you have or are playing with video games. You don't expect to have a benefit out from that, except that you enjoy that, and this is good. You meet other people online, whatever else. But here, the goal is really to improve a specific function. And so the idea is to combine gaming principles with educational or therapeutic objectives. Why is this interesting? Well, first, because it's a multisensory kind of activity. It's a very rich and rewarding and motivating rehabilitation environment as compared to the boring, often environmental setting that you can have in a clinical institution, right? People have fun when they just play a serious game. Why not? It's accessible and inclusive. So if, for example, you think that these serious games can be implemented in mobile devices, well, we're going to have 6.8 billion smartphones by the end of the year. It's a lot. So can you imagine to implement a therapy in the hospital for 6.8 billion people? Imagine the costs. So it's inclusive on top of that. These are cheap methods. It's compatible with training protocols. Or if it's well designed, it can target a specific cognitive or motor function. And it also gives the opportunity to monitor what's going on. The fact that you implement a therapy on a serious game or a smartphone can allow you to control what's going on almost in real time as the therapy unfolds. So there is evidence that the serious game can be used also as a tools for home-based rehabilitation. There is evidence in dementia, schizophrenia, also in developmental disorders. And I'd like to underscore that there seems to be a link between rhythmic serious games and also dopamine. So rhythmic serious games may show potential in treating sensorimotor deficits because we know that musical elements are linked to high reward, and also they can enhance dopamine activation. So there are very good reasons why we should use this approach. So what do we know about rhythmic serious games, or rhythmic games in general? We did a survey. This was already in 2017. Things are changing a lot with time. But at the time, we found that there were a few games already on the market, but they had a lot of limitations. First of all, they were not used for rehabilitation. Their approach is holistic. And there was no proof of concept that basically showed that these games can be used for therapeutic use. I mean, you can download them. You can even play them on a PlayStation, but it doesn't mean that they are efficient in order to induce, to improve a given ability. So we decided to concoct one ourselves. So the game is called Rhythm Workers. This is the first prototype, and it was done with my former PhD student, again, Frédéric Pujarinet, Valentin Begel. The purpose of the game is very simple. You have to tap to the beat of music. It's a tablet game. Basically, you have to build a building. So the better you are in tapping to the beat, the more building will grow. and it's going to be nice. If you do this in a bad way, the building will look terrible. You know, it's going to be even an airplane just going through the building. Yeah, it's more a war situation. But this is an example of the previous version of the game. Yeah, you should hear the music, but I don't know if. Of course, this is my student. He was very good in doing the task. Okay. And so it's a champion, of course. And it goes on, right? So this is the first version of the game. Now we have a much more recent version, which is now being developed by a company, which at the beginning was Network Partner, now this BitHealth. This is available on Google Play and on iCloud. It's called BitWorkers. This is the version available to the public, but it's much more advanced as a game. But the idea is exactly the same. So we use this game, first of all, in Parkinson's disease. It's the first study that we ran. The idea was to do a pilot study in which basically we tested patients before. We trained them for 6 weeks. And then there was a post-test and there was a follow-up. During the 6 weeks, they were playing with the game at home. So it was very easy. You know, patient didn't have to come back to the lab. And so this was 3 times a week for 30 minutes. It's not a huge time play. And we assessed different areas of rhythmic abilities. We assessed from Basta, again, tapping. We assessed gait abilities and also orofacial, exactly the same ability that I mentioned before in the study on Parkinson, and also beat perception. And this is what we found. So what you see here, let's focus on this panel first. So this is the performance of test and retest, so before and after, with rhythm workers. And this is, so the control game was Tetris. It's not the best control in the world, but this is the one that we had at the time. It's still an active game, quite engaging. This is what we used. And so here you see the performance in the articulation task, the vocal task. So when it's, of course, minus means that the variability is very high, and this is better performance. And you can see that basically after rhythm workers, the performance improved. We didn't see much in this specific study in terms of gait variability, although the performance worsened with Tetris, which is probably due to the normal neurodegeneration. That means that, well, patients are getting worse with time. And we had, of course, an improvement in manual abilities, and also when people didn't have a stimulus. So it seems like there is an effect, a near transfer effect to other motor abilities, but the most significant one is really this one. So we didn't train vocal performance or speech articulation, right? So it seems like there is an effect, a beneficial effect of the training on speech. This is an effect that we are now replicating in other populations, but this is still preliminary results, but it seems quite interesting as a result. Another result that we got here is that we wanted to know, okay, is this linked with an improvement of perceptual abilities? We saw before that perceptual beat perception, rhythm perception abilities could predict if somebody was variable or less variable in motor tasks. And so we linked rhythmic abilities to their performance before and after the training. So here what you can see is that basically after rhythm workers, the people get better. in rhythmic abilities. This is not the case of Tetris, which is sort of expected. But the interesting part is that those who improve more in the rhythmic motor abilities are those also who improve more in perceptual abilities. Yeah. So there is a very nice link. People, thanks to the training, got better in tracking the beat, and then they seem to use it in lowering their motor variability when doing the performance. Okay, now I still have, I think, 10 minutes roughly, something like that. I want to present you 2 pilot studies that we just we're publishing at the moment. They are finished, and these were with Hugo Laflamme, is my finishing PhD student here in the. Yes, you, Hugo, and Kevin Jamie, who's really finishing. He's supposed to handle his dissertation by December 1st, so he's not here today. So they ran 2 proof of concept studies in 2 groups, small groups relatively, of ADHD and ASD children. Now, let me tell you that this was done in COVID time. This was 2020. We were supposed to do this in the lab. You all know what happened at the time. So we had to completely convert the protocol into an online version and a remote version. So this was done really in that direction, but it took much longer than we would have liked. And Hugo can confirm here. So first of all, we had to adapt the game, Rhythm Workers, to a developmental population. The game was tailored to basically older adults, Parkinson patients, so there is some work. So goal 1 then was to test the game usability, compliance with the protocol. This has never been done, so we had to test the feasibility of the protocol, completely remote. The goal number 2 was to test whether the game improves rhythmic abilities. This is what it's supposed to do, right? So we train rhythmic ability, we should see an improvement in rhythmic abilities. It's obvious, but let's check the obvious first, and let's make sure that the control task is not also improving rhythmic abilities if we really want to test that. And a corollary goal is to test whether there is a transfer effect to executive functioning. This is very important because we want to check the causality, right? If we train rhythmic abilities, are we going to improve also executive functioning? I say corollary because the groups were still very small. So the results I'm presenting you today are, in a sense, preliminary, very promising though, in that direction. So what did we do? We took, this is for the ADHD group, so 15 ADHD children, 15 ADHD children, a controlled training game. I will show you the game in a moment. It was in a double-blind protocol. The children were tested before via Zoom online. So we had to devise also cognitive tasks online, which were adapted on our testing platform online. And then children played for 2 weeks, 5 days per week, 30 minutes a day. And then we tested them after this period. The training period is not very long, but this is the goal of a pilot, right? I mean, we want to make sure, first of all, the feasibility of that. Behavioral testing, we had BASTA, a very short version, which could be done online. And we had cognitive tasks like cognitive flexibility, inhibition, and working memory. These tasks were done online with one of our experimenters, just making sure that children are doing that. And BASTA was done on a tablet. So what we did, we shipped a package with tablet to each participant all across Canada to do that. And then participants basically shipped the tablet back at the end. So the games were, one is Rhythm Workers, you already know it. And the other one was Frozen Bubble, that you don't know. I'll show you in a moment. So this is a music game, it's a finger tapping game, but there's no synchronization. And actually, we used exactly the same music that we used in Rhythm Workers. So we wanted to control as much as we can in the study. And the testing online was done via our online testing platform, which is a platform, you can take a look at that, it's still on at BRAMS. If you want to do an experiment from a distance, you can still do it nowadays. So here's the new version of Rhythm Workers. Let me show you. You got it. It's certainly funnier than the one that we did in the lab, but this is actually a commercial version you will find online, but the experimental version is very similar. It's enough. And this is frozen bubble. That's the other one.
Frozen Bubble is a free game in the Android market available for your Android devices, and it is a puzzle game in the same fashion as games like Bust a Move. And I'm just going to go ahead and open it up from the web page here.
This is Kevin
You can
Jamie.
see it's a very colorful game, very bright colors. The controls, you slide from side to side here on the bottom, and the goal is to shoot these bubbles into matching bubbles up here. And if you have 3 or more of the same color, then they will disappear. You can see if I shoot this, it's not the same color, so it's just going to stay there. And you can bounce off the walls, make trick shots like that.
Okay,
And,
I think we got it. And actually, we manipulated the game so that to have
Bubble is a free game.
to have more tapping. We wanted to have the number of taps to be the equivalent between rhythm workers. So we this is open source, so we a bit change the game at the end to make it more suitable. So here are some results. I'm going to go fast now. So these are the results about the compliance with the protocol. So people had to play for 300 minutes. So rhythm workers, frozen bubble groups. So, they're quite close to the target. Actually, in frozen bubble, they played even more. So they really liked it. The number of taps is very comparable. The enjoyment is quite comparable. Perceived difficulty is a bit different. It's quite an important point, actually. So what you can see here is the enjoyment rating that they provided for the 10 sessions. It's pretty stable in both cases, above the average. Difficulty was a bit more difficult for rhythm workers. It seems like that the difference probably here just reduced, but still the difficulty was consistent across the 10 sessions. So we saw an effect on rhythmic abilities as expected. So here is in rhythm production, so in the tapping task, frozen bubble, rhythm workers, we see, so what you see here is a different score. When you get 0, it means that there's no improvement post-test versus pre-test. And we see that there is an improvement only for rhythm workers. And even this is more even visible for tapping to music, which is obvious because this is what we trained. Right? But people didn't improve in frozen bubble. Interestingly enough, we see a tendency towards an improvement in rhythm perception. This didn't come out significant. These are very small samples, though, but it's quite promising. It seems like also it seems to impact rhythm perception. It's a dose-dependent effect. So those who played more are those who basically improve more. But of course, this is not the case for frozen bubble, right? You see that the blue dots are those for rhythm workers and yellow for frozen bubble. So what about executive functioning? Well, there is a significant effect. In this case, it was not the best possible situation to show an effect because the training was very short, just 2 weeks, but we still see a promising effect of rhythm workers only on execution functioning. This is a composite score between flexibility and inhibition, but we see that basically we have a moderate effect size here for just this very small sample. So it's promising, certainly. So we have high compliance, which definitely exceeds the expected rate for pediatric mental disorders. We have above average enjoyment and engagement. Rhythm workers is successful in training abilities in ADHD children. And we have a tendency towards an enhancement of executive functioning. We have to take it, with a grain of salt, but it's still a promising result. What I'm going to show you now, and then I will stop, just a few more slides, is these are results from another study with rhythm workers in autism spectrum disorder. Exactly the same protocol, exactly the same amount of participants. We actually conducted one study after the other. We just improved a bit the game because, we wanted to learn from the feedback from the first group of children. We observed quite high compliance, a bit lower than what we observed with ADHD, but well, the population is certainly more difficult. But we have average and comparable enjoyment and perceived difficulty. Actually, in this case, we don't have a difference of difficulty between the two, at least not significant. But the good news is that in 2 weeks, participants were still playing the game with the same degree of enjoyment, which means that it can be continued afterwards if we want to have a longer training. We have an effect on rhythmic abilities like before. So we have a significant improvement of rhythmic abilities following rhythm workers, not following frozen bubble. And again, this effect is a dose-dependent effect. The more children play, the greater the effect of the training on rhythmic abilities. Now, the cherry on the cake would know, okay, do we have an effect on executive functions? Yes, we do. It's again, it's a combined score between flexibility and inhibition on accuracy in this case, but we see an improvement. I treat this as a preliminary, although significant result, but it's very promising to lead to further studies. So let me wrap up quickly. So in this talk, I wanted to show, okay, how we measure rhythmic abilities, what they are, how people differ. This is so common to have rhythmic disorders in clinical populations. And the second part is, okay, how can we train these abilities? Can we do it, first of all? And can we do it using serious games? And can this lead to effects on transfer effects on other motor abilities and to other cognitive abilities? So it seems like rhythmic serious games are an interesting alternative, easy to implement in both neurodegenerative and neurodevelopmental disorders. These proof of concept studies reveal that the game are usable. There is good compliance, especially in the neurodevelopmental groups. And so they are quite feasible. They can, all of them, increase rhythmic abilities. There is a dose effect, which is, in a way, witnesses of the specificity of the training. And then we can have transfer effects towards motor abilities and preliminarily also towards executive function. Now, what we need to do now is to do more studies, plan future RCTs, and also try to inquire more about the neuronal substrates of these effects. So, of course, this is not one-man work. Some of my students are here today, so there are a few students involved in all these studies and also a bunch of collaborators from Canada, France, Germany, the Netherlands, and Australia. I thank the funders, and I thank you for the attention.